So after we learn about the binomial probability distribution, now it's time to learn about another discrete probability distribution, and that is the Poisson probability distribution. The first objective is to determine if a probability experiment follows this model. We use this Poisson probability distribution to compute the probability of an experiment in which the x random variable counts the number of occurrences or the successes for a particular event within a specified interval. So this is the keyword. So it has to be within a specified interval, and the interval could be a time or the space. Now, there are a few criteria for this model. So we let x to be the number of successes in a fixed interval. So x is a random variable. Now, the first requirement for this model, this process, is that the probability of 2 or more successes in any sufficiently small subinterval is 0. So for example, I say here that we consider a fixed interval. So let's say the fixed interval for the timing between 0 and 5 minutes. And now we consider a small subinterval. So the small subinterval could be 1 to 2 seconds. And the fixed interval is 0 to 5 minutes. And the small subinterval of that could be 1 to 2 seconds or 3 to 4 seconds. So make sure that the probability of 2 or more successes in any sufficiently small interval is 0. And then the next requirement, the probability of the success is the same for any 2 intervals of equal length. So let's say that we have the interval from 1 to 2 minutes, and 2 to 3, and 3 to 4, and 4 to 5. Make sure that the probability of the success is the same for any 2 interval of equal length here. And then the last requirement, we want the number of success in any interval is independent of the number of success in any other interval, provided that the intervals are not overlapping. So from 1 minute to 2 minutes, 2 to 3, 3 to 4, make sure that the number of success in those intervals, they are all independent. And make sure that all the intervals, they are not overlapping. So if you can get all the 3 requirements here that are satisfied for the problem, then we can apply this model, the Poisson probability distribution, to that problem. Okay, let's now take a look at the example. So we have the first example here. A McDonald's manager knows from prior experiment that the cars arrive at the drive-thru at an average rate of 2 cars per minute between the hours of 12 noon and 1 p.m. So in this problem, we are given a fixed interval, so you could consider using the Poisson probability distribution. Now we let x to be the random variable. This is the number of the cars that arrive between maybe 12:20 and 12:40. And this model, this event, would follow a Poisson distribution. So make sure you pay attention to the interval given in the problem, and we can apply the Poisson probability distribution. Okay, the next objective is to compute the probability of a Poisson random variable. Now let x to be the number of success in an interval of the fixed length t. We have the formula to compute the probability using this model. P of x equal lambda multiplied with t all to the power of x over x factorial multiplied by e to the power of minus lambda t. Now this notation here is the Rick notation, and this is the lambda. Okay, and your x is your discrete random variable from 0, 1, 2, 3, 4, 5, and so on. The lambda, this is the average number of occurrences of the event in some intervals of the length 1. And then the number e here is a natural number. It's equal to 2.71828, and so on. So for example, go back to this problem here. We have the average rate of 2 cars per minute, 1 minute, between the hours 12 noon and 1 p.m. So in this case, the lambda should be 2 cars per minute, and lambda is the average number of occurrences. We have 2 cars occur between a fixed interval and 2 cars per minute, and the timing here is 20 minutes because we have 12:20 to 12:40. So the timing for this fixed interval is 20 minutes, and the average value is 2 cars per 1. So this is the occurrence of the event in the interval of the length of 1. Okay, now let's try to go over one example for finding the probability of an experiment using this process. We use the same example of the McDonald's managers. So this manager knows that the cars arrive at the drive-thru at the average rate of 2 cars per minute between the hours 12 noon and 1 p.m. Determine and interpret the probability of part A. Exactly 6 cars arrive between 12 noon and 12:05 p.m. So we have the interval of 12 noon and 12:05. So this interval here will give you the fixed interval of 5 minutes, or the timing t should be 5. And we are looking for the probability of 6 using the Poisson process. And we know that on average we have 2 cars per minute, and that is the value of the lambda equal 2. And as we saw earlier, the probability p of x is given by the formula lambda times t all the way to the power of x over x factorial e to the minus lambda t. Now in this case, we have that lambda to be 2, the timing t is 5 here, and then you are looking for x here, exactly 6 cars, so we are looking for x to be the value of 6. So you plug in 6 for the random variable x over 6 factorial, and then multiply e to the minus lambda. Lambda here is 2, and then t is 5. And then if you perform the calculations here, you should get 1 million over 720 for this factor, and then e to the minus 10, which give me 0.0631. So that is the answer, 0.0631, and we can convert it back to percentage, and you can move it 2 places to the right, so that should be around 6.31%. So how do we explain the meaning of this answer here? So 6.31% or around 6%. So that means for every 100 days, there are about 6 days, exactly 6 cars will arrive between the time of 12 and 12:05 p.m. So 6% means 6 days out of 100. So on average, about 6 days for every 100 days, we have exactly 6 cars that will arrive between the time of 12 noon and 12:05 p.m. at the drive-through gate for the McDonald's. Okay, so the next part, we are asking to find the probability of fewer than 6 cars that will arrive between the 12 noon and 12:05 p.m. Now, this is the same time interval from 12 noon and 12:05 p.m. So we should get the same time interval of 5. And we also have the lambda. It's also the same thing as before, 2. And now we are asking to find p of fewer than 6. That means p of random variable x less than 6. Now, the question asks you for fewer than 6. That means you don't want to include the equal sign here. So x less than 6 here is the same thing as x is less than or equal to 5. This is the same equivalent statement here. And p of x is less than or equal to 5 is the same thing as p of 0 plus p of 1 plus p of 2 plus p of 3 plus p of 4 and plus p of 5. So anything less than or equal to 5. So we start from 0, 1, 2, 3, 4, 5. These are the discrete values. And remember, x here starting from 0, 1, 2, 3, 4, and so on. So you want to add all of them up to the value of 5. Now, we can do that here for each individual p of 0, p of 1, p of 2, and then we sum them together. So for example, p of 0, all we do now is we plug in 0 to the place of x right here in this formula. So p of 0, we will get, this is 2 times 5, and to the power of x, and x now is 0, over 0 factorial. 0 factorial, remember this is the value of 1. This is by the definition of the factorial. And then e to the minus of 2 times 5. And we will have to do the same thing for p of 1, p of 2, and p of 3, and p of 4, and so on. So p of 1, so we have 2 times 5 to the power of 1 over 1 factorial, and then e to the minus 2 times 5, and then p of 2 equal 2 times 5 to the power of 2, 2 factorial, e to the minus 2 times 5, and then so on. And then once you find all the value of p of 3, p of 4, p of 5, you will add all of them together, and then the answer should equal to 0.0671, and that is the probability of finding a fewer than 6 car arrive between 12 and 12:05 p.m. And if you are converting it back to percentage, you should get 6.71%. So that is closing to 7%. So you can expect that for every 100 days, about 7 days, fewer than 6 cars will arrive between 12 noon to 12:05 p.m. Okay, the last part for this question is finding the probability that at least 6 cars will arrive between the time 12 and 12:05 p.m. So now in this one, we are looking for p of at least 6 cars. That means x is bigger than or equal to 6 cars. And we can use the complement rule to solve for these questions. Now, p of x is bigger than or equal to 6. That means you want p of 6 plus p of 7 plus p of 8 and so on, all the way to the right. But these are a lot of different numbers that you should find. So instead of finding all of them and adding together, which is very difficult things to do, we can use the complement rule to do that. You can write p of x is bigger than or equal to 6 as the same thing as 1 minus p of x is less than 6. Remember, everything when you add them together, you should get 1 for the total. Now, to find anything bigger than or equal to 6, you just take 1, subtract for anything less than 6. So imagine that you have the number line system here. You have 0, and you have all the way maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. The probability of everything on this number line here should equal to 1. And for example, this is 6, it's right here. So now you want to look for all the value from 6 and above. Okay, so you are looking for the value here in this region here. So all you do now, everything is 1. So you take 1, you subtract for anything less than 6 to get this portion right here. So 1 minus p of x is less than 6. This is the complement rule. And we found this one earlier in part B. And we got the answer of this one in the last part, which is 0.0671. And that should give me 0.9329. And if you convert it back to percentage, you should get about 93.29%. And to explain this answer right here, 93 is about 93%. So you can say that on about 93 for every 100 days, at least 6 cars will arrive between the time 12 and 12:05 p.m. Okay, so now let's move on to the last objective of this section, to find the mean and the standard deviation of the Poisson probability distributions. Now, consider the last few examples. We have the 2 cars per minute arrive at the McDonald's between the time 12 noon and 1 p.m. Now, how many cars would you expect to arrive between the time 12 and 12:05 p.m. considering that the 2 cars arrive every minute on average? We had that, and we are observing the arrival of the cars for 5 minutes, 12 and 12:05 p.m. So we multiply the two cars per minute for 5 minutes to get 10 cars. So 10 cars will arrive between 12 and 12:05 p.m. Now, the expected value of a random variable is the mean of the random variable. So it is reasonable to say that the mean or the expected value is equal to the average value multiplied by that time interval, or the expected value should equal to the lambda multiplied by t, and t is the length of the interval. And then to find the standard deviations, we can take the square root of the mean. So take the square root of the lambda and t to get you the standard deviation. So the expected value of x is the mean of the random variable x, which is a lambda times t, and the standard deviation is equal to the square root of the lambda times t. So these are the 2 formulas we are using of this model, the Poisson model. Okay, and remember that we got the formula p of x equal to the lambda t to the power of x over x factorial e to the minus lambda t. Now the lambda t now is the expected value of x, which is mu value. This is the notation of mu. So instead of writing the lambda t, you can just simply write it as mu to the power of x and e to the minus mu. So this is the simplified version of the probability of the Poisson distribution P of x. Okay, let's move on to the next example. Consider this example. A biologist performs an experiment in which 2,000 Asian beetles are allowed to roam in an enclosed area of 1,000 square feet. The area is divided into 200 subsections of 5 square feet. Now, part A. If the beetles spread evenly throughout the enclosed area, how many beetles would you expect in each subsection? So that is equal to the expected value, and that is the value that you got the notation of mu of x earlier, and we got a total of 2,000 beetles. So we got 2,000 beetles, and we have 200 subsections, so divide that on average, 200 subsections, and that will give me 10 beetles per subsection. And that is your expected value for the number of the beetles in each subsection. The next question, they are asking you to find the standard deviation of the random variable x, which is the number of the beetles in a particular subsection. And according to the formula you saw earlier, the standard deviation is equal to the square root of the expected value, or you got here is 10, and that should give me around 3.2. And then now we have the last question. What is the probability of finding exactly 8 beetles in a particular subsection? So we know that we are using the Poisson distribution, and we can find P of 8 because we are looking for exactly 8 beetles. So P of 8, and you got the formula. So let me rewrite the formula. P of x is equal to mu to the x over x factorial and e to the minus mu value. That is the mean value. So this is the simplified formula that you just saw earlier. And your mu, the expected value, you got from part A, which is 10, and now you want to find the when x is equal to exactly 8 beetles. So you got 10 is your expected value to the power of 8 over a factorial and e to the minus 10. This is from part A. And if you do the calculation, you should get 0.1126. Okay, and that is around 11.26% or 11%. Now, how do I interpret this answer? So 11% means that in 100 trials of the study, we expect to find 8 beetles in a particular subsection about 11 times. So let me write here. So in 100 trials of the study, we expect to find about exactly 8 beetles in a particular subsection about 11 times. And okay, now we have the last part of this question, part B. Would it be unusual to find more than 16 beetles in a particular subsection? So they are looking for P of the random variable x to be bigger than 16. So you are looking for if this is unusual to find more than 16. beetles in a particular subsection. So what we can do now is we are looking for the probability of x is bigger than 16. So now we can find this by using the complement rule. So p of x is bigger than 16 is equal to 1 minus of p of x is less than 16. Because it is difficult to find p of x is bigger than 16. It could be 16, 17, 18, 19, 20, and so on. So you have to add all of them together. But instead of doing that, you can take the total sum of 1 minus of anything less than or equal to 16. And we can find p of x is less than or equal to 16 to be 0.9730, and you should get the answer of 0.0270, and that is about 2.7%. And you can round it up to about 3%. And this number is telling you that according to the Poisson probability model, there will be more than 16 beetles in a particular subsection about 3 times for every 100 trials of the experiments. And to observe more than 16 beetles in a particular subsection is unusual because this is a small value. Now, how do I find this value using the TI-84 calculator? So to use the TI-84 or 83 calculator, you can use the command Poisson, the function Poisson CDF. We are looking for anything less than or equal to 16. So this is the cumulative value. So cumulative stands for has the value of the letter of C. So we are using the Poisson CDF instead of PDF function. So the first input, the first argument here is we are putting the expected value, and the expected value mu of x, and the next value is the number of the successes or the random variable x to get you the p of x is less than or equal to 16. In this case, we got the expected value from part A, which is 10, and the x value is your number of successes, in this case 16. Remember, the expected value is equal to the lambda times t. In this case, part A gives you 10. So Poisson CDF of that will give you the value here. Now I'll show you quickly how to use that here. So we can use that by using the distribution. So second var to get you to the distribution list, and then scroll down all the way to Poisson CDF, because we are looking for the cumulative value from 1, 0 up to 16. The lambda value here is actually the expected value, not the single lambda as you saw, but that is the mu value instead of the single lambda. So the lambda's notation here is your expected value, which is 10, and your x value is the number of successes. In this case, it's 16 beetles. We are looking for 16. So enter 16 here will give me the value that you saw here, 0.9730. And then you can also use Excel. So how do I use the Excel? Now click on the formula tab and click on insert the function, and we are using the statistical, and scroll down to Poisson distribution. So Poisson.dist distribution, and then in here the x value is your number of successes, in this case 16, and the mean value is your mu of x or expected value. In this case we have 10, And then we are looking for the cumulative value from 0 up to 16. So you want the cumulative. So in this box, you type true. Yes, I want that. And click OK. And that is your P of x is less than or equal to 16, 0.9730. And if you just want to find a single value, but not the whole cumulative value, then inside the cumulative box, you just type the false argument instead of true. And that is the end of this section 6.3.